Okay, so I've decided to talk about and provide rationale and attempt to remove, reduce, lessen, and get rid of all sorts of confusions pertaining to in the minds of students as to why this and this end up uh, uh, in this, get imprisoned in this relationship to yield this. So let me just say very simply that when you are doing calorimeter, calorimetric experiments to find out either the specific heat capacity of the fluid that's warming the known metal of known specific heat capacity, or you're trying to numericalize or quantify the specific heat capacity of the metal that you're using. It could be aluminium, copper, tungsten, iron, lead, zinc, anything. When you're trying to either find out the specific heat capacity of the fluid medium or the metal, you have to use this formula because this circuit, and I've added three capacitors in parallel as a joke for those who may be able to appreciate it. This circuit is supplying power for both these systems. So in this system, this circuit is providing power for both these components. The component of the metal being warmed by the use of a metal coil around it, and the thermometer registering, recording it, and then the fluid experiencing the heat coming from the coil, heating the metal, and then the temperature change taking place as a result of the increment of average kinetic energy of the fluid, leading to a higher rate of bombardment against the walls around the metal and within itself, so a higher rate of collisions of intra and intermolecular collisions due to work being done upon them due to the supply of heat energy. So, which is why we have to use this. So I times V times T equals mass of the metal times specific heat of the metal, known and unknown, and then the temperature change. Now the funny thing about temperature change is that what you could do is um you can just you look the temperature change the degrees of difference is the same. Now Kelvin and Fahrenheit and Celsius are very, very different due to the scalings and graduations, but 25 degrees to 50 degrees is the same as 273 to 298. I hope you understand. So you just need to find out how much difference is, and then you can just put that in, and that'll be mass of the immersed object times the specific heat of the immersed object times the temperature change experienced by the immersed object plus the mass of the surrounding fluid media times the specific heat of the surrounding fluid media times the temperature change the fluid medium has experienced whilst providing a heating medium to the um, metal. Now, you might ask me a question that, look, why do we need to use a fluid medium when we can just simply wrap the coil around? Yeah, wrap the coil around, and then we can heat the copper, or in this case zinc or tungsten or iron or lead, or gold or silver or platinum, just by wrapping the coil around. Well, you're right, you're correct, but we may need to do it in some cases. It's just how it's taught at A levels. You can do it without the fluid medium, but they wanna induce a layer of complexity to harmonize the layers of understanding that go into resolving numerical questions at A levels and sixth form caliber, post 16 caliber. So this is why most questions will always contain a bomb calorimetric setup with the fluid and the metal bar, whereas theoretically speaking you could just stick but then again, let me just say, fluids do minimize eddy currents, magnetic heating, and mechanical resistances that may occur whilst the fluid is not there. And for experiments where you want to know the specific heat capacity of the fluid, that's when this circuitry would come in handy. So it's a way of enhancing learning, and also to inducing a higher level of complex problem solving skills amongst the students, and to bring the brightness out of the dedicated physicists. So here's a joke: three capacitors in parallel, and what else? Da, da, da. So KG. Okay, I think it's about time. It's time to end this video. Cheers.